Hello students, welcome back. Previously we completed up to 3.2. Now let's go to 3.3 and discuss Wilson's theorem again. I know we already went through Wilson's theorem in lesson 9 after Fermat's theorem, but Wilson's theorem is important enough so that having one more proof and different viewpoint will not hurt. And also, the polynomial congruence is an important topic as well, so having an application in very different viewpoints will not hurt either. So let's have 3.3 as a digression, and then we're going to come back and discuss 3.4 in a separate video. Okay, this is Wilson's theorem. P minus 1 factorial is congruent to -1 modulo prime, or equivalently p minus 1 factorial plus 1 is congruent to 0 mod p, either way. Alright, we're going to use polynomial congruence, so we're going to define a certain polynomial cleverly. We'll define it like this. X minus 1, x minus 2, x minus 3, x minus 4 up to x minus p minus 1, obviously for p minus 1 factorial, and then subtracted by Fermat polynomial, x to the p minus 1 power minus 1. Okay, alright, and if I expand it out, then we're gonna get x to the p minus 1 power. Yeah, the only way to get p minus 1 power is get x, 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 and all x, and they all have coefficient 1. And then we'll have lower degree terms. And then subtracted by this Fermat polynomial. So what do you have? P minus 1 powers kill each other's off, and we're gonna get a polynomial of at most, p minus 2 degree. And then let's apply Fermat's theorem. Plug in 1, 2, 3, 4, 5, 6 all the way up to p minus 1. Well, if I plug in 1, 1 minus 1 is going to be 0, and 1 to the p minus 1 power minus 1 is 0. If I plug in 2, 2 minus 2 is going to be 0, and then 2 to the p minus 1 power minus 1 is 0. Plug in anything, something minus something, that's going to come down to 0, and we have Fermat's theorem. So they're all zeros. F of 1 is 0, f of 2 is 0, f of 3 is 0, all the way up to f of p minus 1 0. They're all zeros. So this f of x has p minus 1 zeros, and this is supposed to be a polynomial of degree p minus 2. That can't be right, right? I mean, we have p minus 1 0 spelled out, all these, but degree is p minus 2. That can't be right. It contradicts Lagrange's theorem. It cannot be right unless this itself is a 0 degree polynomial, a 0 polynomial rather. So coefficients are all 0. In other words, this thing and the Fermat polynomial must be the same. This is all 0. The same modulo p rather. So x minus 1 times x minus 2 times x minus 3 up to x minus p minus 1 minus this Fermat polynomial is congruent to 0, or equivalently, this product is congruent to the Fermat polynomial of x to the p minus 1 power minus 1 is congruent modulo p. We're almost there. Here, if I plug in 0 in place of x, I'm gonna get yeah, I can plug in 0, but looks like on second thought, plugging in p is gonna be more convenient. This way I do not have to worry about any of sign changes. Well, p is congruent to 0, so actually no problem there, but if I put in a lot of zeros in there, then we have too many sign changes, too many negatives flying around. So I think this is a bit more convenient. Put p in place of x. So this is 1, and then that's 2, 3, 4, all the way up to p minus 1, starting from the right. And right here, p to the p minus 1 power, but p is congruent to 0 modulo p, so we just get negative 1. So p minus 1 factorial is negative 1 modulo p, and that's precisely what we wanted. That's a conclusion of Wilson's theorem. So the starting point here, getting this polynomial was a neat idea. X minus 1 times x minus 2 times x minus 3 up to x minus p minus 1 minus this Fermat polynomial. But once you get that, it's easy. We have p minus 1 solutions, or p minus 1 zeros by Fermat's theorem. But that contradicts Lagrange's theorem because this has polynomial of degree at most p minus 2 unless coefficients are all 0, so we get 0 polynomial. So this is 0 polynomial, so this product and then Fermat polynomial are congruent, mod p, and then plugging in p, we get this conclusion. Alright, we went through a neat example in Wilson's theorem, and this way we utilized Lagrange's theorem once more. Now we have a lot of time left, but I'd like to have 3.4 in a separate video as a start fresh. So let's stop here and let's meet again in a separate video for 3.4.